So we'll quickly go through the S2 Edexcel May 2015 paper, question by question. In question 1, in a survey, it's found that barn owls occur randomly at a rate of 9 per 1,000 kilometers squared. So the word rate, and we're obviously looking at 9 per 1,000 kilometers. Those are clues that we're definitely going to be working with the Poisson distribution, and we'll see where that takes us. Part A, find the probability that in a randomly selected area of 1,000 kilometers squared, there are at least 10 barn owls. Firstly, I want to check whether this area matches up with the area that we had originally. 1,000 is something I wanted to see. 1,000 kilometers squared, there's at least 10 barn owls. Okay, so using the Poisson distribution, firstly, X is going to follow a Poisson where the lambda value is 9, and this is per 1,000 kilometers squared. It is actually just a simple probability. Probability, at least the smallest amount of barn owls should be 10, so X is greater than or equal to 10. This is a cumulative probability, so we're going to want to use our tables, but our tables will not help with greater than statements, will not help with greater than or equal to statements. So a 1 minus X is less than or equal to 9, and this is something we should be able to look up in the tables. It won't be a 10, because if 10 is included in the original probability statement, it cannot be included in the amount that we're going to subtract from 1. So this is going to leave me with 1 minus 0.5874, and the answer to that is 0.4126. Okay, moving on to part B of the question. Find the probability that in a randomly selected area of 200 kilometers squared, there are exactly 2 barn owls. Okay, I've spotted that this is now different. It's not going to be the same value for lambda. We're looking at only 200 kilometers squared rather than 1,000. So now, X is going to follow a Poisson distribution of 9 divided by 5, which is going to be 1.8 per 200 kilometers squared. Probability that X equals 2, so exactly 2. 1.8 is not in the Poisson tables, so that indicates I'll be using the probability function itself. So the probability function is e to the minus lambda multiplied by lambda to the power of x, all divided by 2 factorial. Plugging this into your calculator, we should get 0.2678. And so if we scroll down now to the third part of the question, part C, using a suitable approximation, find the probability that in a randomly selected area of 50,000 kilometers squared, there are at least 470 barn owls. First, let's choose an appropriate value for lambda. Since for 1,000, it was a value of 9, for 50,000, it's going to be 9 times 50. X is going to follow a Poisson of 450. The only approximation that I can go to from the Poisson is a normal approximation. One of the conditions, or the condition to go to the normal approximation, is that I have a large value of lambda. 450 we will consider to be quite large. So, approximating to the normal distribution, Y will follow a normal distribution. The parameter for mu will be that value of lambda, and the variance, which I'll put in this form, standard deviation squared standard deviation being the square root of 450, is as shown. The probability that I was asked for. Moving on to part C, we've been asked to use a suitable approximation. The approximation here, from the Poisson, I can only approximate to the normal distribution, and it does follow the condition of lambda being large. Moving on to part C, I know that I've been asked to use a suitable approximation, so we'll just look out for what happens there. Firstly, now that I have an area of 50,000 kilometers squared, I'll start with x follows a Poisson distribution where the value of lambda is going to be 9 times that 50. 9 times 50, 450. This makes sense to approximate since the value of lambda here is large. If I were to approximate, and I'll write this as y follows a normal distribution where the mean is going to be lambda and the variance is going to be 450. I'm going to write it in the form root 450 squared, so I can easily see the standard deviation is root 450, which I will use later. This Poisson distribution, which was per 50,000 kilometers squared, I've been asked to find the probability that there are at least 450 barn owls. So the probability that x, the smallest value, should be 470. So x is greater than or equal to 470. While if I use the normal, which is a continuous distribution, I have to have a continuity correction. Thinking whether I'm going to include 470 or not, I know that I must include 470, so y is going to be greater than, we can have an equal to, 469.5. Just double checking, did I want to include 470? Yes, I did. Does this statement include 470? Yes, it does. I'm happy that I've applied the continuity correction correct. From here, we're going to go ahead and standardize using the standardization formula. So the probability that z is greater than or equal to my x value minus the mean of this distribution, that's the 450, divided by the standard deviation, that's the root 450. Be careful to write the standard deviation squared whenever you state the normal distribution, just to make sure that we get this correct value in the denominator. Okay, we'll go ahead and plug that into the calculator, and that gives me a z-score of 0.9192. Okay, so we're going to need our normal distribution tables, a quick sketch of this situation, when standardized, I'm trying to find this probability over here, which should be quite a small probability. My tables are not set up to help me find that. My tables, however, do find the probability that it is less than that particular value. So a 1 minus statement is going to help me to find the specific area that I'm looking for. So 1 minus 0.8212, and that should equal 0.1788. That's the probability we're looking for.